Intel's next-gen processor Panther Lake continued the tradition of the disaggregation multi-tile approach that we have seen on Lunar Lake, Meteor Lake, and Arrow Lake. I'm Alejandro Hoyos, and in this episode of Talking Tech, we take a closer look at how we actually went from monolithic approach all the way to multi-tile approach, and also taking a look at advanced packaging and how this played a pivotal role in order to achieve these goals. Join me in the road of Panther Lake.
When you disag the processor into chiplets, there's several benefits. One, you can ramp new process nodes faster with better yields with smaller die. The demands of the PC market have both fragmented and grown, and this allows us to build SoCs that are perfectly tailored using chiplets to meet the market needs. And you're going to see Panther Lake systems in more products and more segments for AI PC than we've ever done before.
I've been here for 20 years. I joined in April of 2005, and I am the director of Foveros. So I manage the team that does all of the TD work for internal and external customers on our Foveros line.
For those people who don't know our acronyms, what is TD?
TD is Technology Development.
Technology Development.
Yep,
Okay,
all the
cool.
R&D.
My name is Yaron Alankri. I am the general manager of the client design group that we're responsible for designing Panther Lake.
My name is Ari Gichon. I'm an SoC lead architect for the client market. This includes memory subsystem, it includes fabric, it includes IP integration, power management, debug, and so on. So all the components of the SoC integrated together and bringing a chip eventually.
What is disaggregation? Disaggregation is what we use to do a mix and match between dies where we want to put the transistors. Have several reasons why we disaggregate the dies. First is we select the best process for usually for the CPU and for the transistor that we need to run fast. Usually we put them on a leading node.
We shifted to a disaggregated type of construction in order to meet and solve some of the constraints that we have. Some of it are with regards to process scaling and the ability to actually produce very big dies. Remember that we are building a much bigger dies with bigger graphics. We have the NPU, which is huge. We have the amount of cores are increasing every generation. You need to continue and scale. And if you want to scale, one of the solutions is going with the disaggregated architecture.
All right, so the last couple of years, we have seen that the industry has moved into, especially at Intel, we have this multi-tile approach in which we have different tiles that have different SoCs attached to it. But before we jump into that, what is packaging?
So when silicon comes out of the fab, it's in its wafer form. So there are hundreds, if not thousands, of single CPUs that are printed on each wafer. And so somehow we need to get those wafers to the end product that a customer can solder to their motherboard. So the process of dicing all of the CPUs into their individual components and then placing them on a substrate or in a form that a customer can use, that's called packaging.
Okay, so that's the packaging. Yeah, there's I guess, I don't know, there's little wires that go into the...
So we used to do wire bond. I would say that's probably ancient technology. So now we use, I think something a little more recent would be like a flip chip BGA, which means that we put bumps on them and then flip them over and then place them onto a package. So even that technology, we still use it today, but it's a little bit older, probably something from maybe 2012-ish is when we started to turn over to more advanced packaging. So traditionally, our flip chips are single layer. So it's a single piece of silicon that does everything. And it's kind of like a one-story building. You can have multiple chips on a package. Sometimes they do different things, and then sometimes they start talking back and forth. So right around 2012, 2013 with Haswell, that's when really I would say we kicked off, or maybe is the origination of advanced packaging. So once the chiplets start talking back and forth to each other, then you can have them talk back and forth in many different forms. And that's really the start of advanced packaging. But I would say maybe wire bond and maybe that single story flip chip, those are the traditional packages that we used maybe early 2000s, maybe 2010, 11, 12. And then from then on is really when advanced packaging started taking its, really started taking off, yeah.
Was Haswell, was that a communication between like the processor and the SoC? Was that the direct? Okay.
Right, so we had a processor, and you can have multiple processors on there, and then you also have a PCH. So that's also kind of the start of disaggregation. So we took the PCH out of the silicon and put it as a second die on the package. And then they started talking back and forth between each other. So that was really, I would say, the start of disaggregation in its really simple form.
That's pretty. Can you tell us, it was starting from there, I guess, how has it been the evolution from then all the way to what we have today?
So we started with like an FCBGA, PGA, LGA, just the single story. Then we started moving into EMIB. So with like Haswell, with the chips talking back and forth to each other, they're really talking back and forth through the substrate. And you are bound by the substrate design rules. So like line and space, things like that can limit your bandwidth, can limit your latency, things like that, limit your power. So to get them to talk faster, we developed EMIB. And EMIB is where you embed a piece of silicon into the substrate, where now your connection, instead of having to be on the substrate design rules, which are a little more coarser, a little bit slower, you can put it on silicon. And now silicon, of course, has its lithography. You can get the line and space super tight, so you can have a very fast connection between the die that goes through the substrate. So from EMIB, then we jump into Foveros and one of our newer technologies, which is HBI. So Foveros, you can think of, is now you're starting to split your die up into its individual components, and you stack them on top of each other in like a 2.5 or 3D. So you're taking chiplets and you're stacking them on top of a silicon interposer. And the interposer, it can be active, meaning that there are transistors and active components on the bottom, and that's considered 3D, or it can just be passive, and you can use it as a very fast conduit for all the chiplets on the top to talk to each other. So we do 2.5D, which is a passive interposer, and we do 3D, which is an active interposer. And then on top of that, starting with our Panther Lake product, you can take those stacked die and you can also EMIB them together through the substrate. So there's a lot of different forms of advanced packaging and disaggregation. So, and Panther Lake was really our, I would say, the first one that was fairly integrated and complicated, where it just combined everything together.
Yeah, it sounds like, one of the great things about this is you can actually use all of them together, like you said in Panther Lake, all the different types of one, or you can just stick to one. So now jumping over to the client side, we have different types of technologies when it comes to packaging. We started with Haswell, and then we are up to, I think, today Foveros. Can you tell us like how it evolved and kind of a little bit of the technology that are?
Sure. So starting around 2012, we had Haswell, where the chips, you had multiple chips on the package, and they talked to each other through the substrate. We had a couple of generations there, Cannon Lake, Ice Lake, Raptor Lake, where we utilized that technology. And then starting in Meteor Lake is where we jumped to the Foveros technology. So Meteor Lake, Arrow Lake, and Lunar Lake all use Foveros 2.5D. And at Intel, our client computing group, CCG, is the #1 utilizer of Foveros. We have probably a little over 100 million units that we've processed to date.
Wow, that's a lot of units, and again, it makes sense because you have all these processors out there throughout different generations. So it's pretty impressive. So what are the different advantages that Foveros brings to the table compared to previous technologies?
So if let's talk in maybe terms of our client computing group, CCG. They make all of the products for what you and I would purchase in a laptop, for ourselves or for our kids, what we use every day for work. They're the #1 consumers at Intel for the Foveros technology. So where they were going, their silicon was getting, slowly larger and larger and larger. And in client, the I would say something they're extremely concerned about is form factor. So X and Y, and then also in Z, because you always want a thin laptop or something that's very light. So their silicon was growing larger and larger to the point where the form factors were getting a little bit too big for what they were trying to use it for. So if you can't grow out, you have to start growing up. So for what Foveros allowed them to do was get back into more reasonable form factors, but still not have to compromise on performance or capability or the different aspects that they wanted to put into their products. They could still do that. They could mix and match many different chiplets on the top and still get what they needed at a lower cost and in a lower form factor and a smaller Z.
Disaggregation comes to actually solve several problems that we have and add additional flexibility. The flexibility can be in the size of the dies that you can actually produce. The flexibility can be in the mix and match of the different dies that we want to do. If you want to do different processes, different sizes of graphics, it's just easy. Imagine it's a Lego and you build a chip. With monolithic, you build one part of the Lego and everything is inside. It has good things and it has some disadvantages. It can have some goodness with regards to latency. It can have some goodness with regards to building everything together and behave coherently. But it's also hard to build things in scale. If you want to build many permutation of the same things with differences, then disaggregated architecture is the right way to go. So I would say you would see both of the architectures we said coming from Intel.
So in order to have a reasonable cost for the product, which is always challenging, you need to select where to put the transistor and do the best mix and match between processes, okay? So usually we put where we need the fast transistor on the leading node process. And for example, IOs, which they have a fixed frequency, can be used on a N-1 or N-2 process. The second thing is that we look at the architecture scalability. When we build the building blocks and we can define how to build the family by these building blocks. So this is another good reason to do disaggregation. One of the aspects of disaggregating is that you control the die size, okay? You don't have a huge part. Die size, when it's big, usually it's reflecting to lower yield. So smaller dies have a better yield, and especially when you go to the leading node, you care about yield. So this is another reason why disaggregated is important.
The technology kind of builds on itself generation over generation. So you start with something that is a little bit coarser pitch. 55 micron, I would say, is probably still fairly standard right now, but as we have moved on in over the years and over the generation, the pitch is getting smaller and smaller. You can pack more die. So while the pitch is getting smaller, the complex is still getting a little bit larger because now you have a technology where you can mix and match. So you can take a bunch of different things and customize it for whatever a customer wants across many different fab nodes. Mm-hmm. You can combine them all onto a single base die and have it work as a custom package for a customer, or you can just continuously start adding more and more to get more features.
So one of the reasons, I guess, that we have come to disaggregation, it's related to yield, right? So
right.
How does that work?
So when we create wafers in the fab, they have a certain defect density. Mm-hmm. It's pretty standard. So the larger the die gets on the wafer, the more likely that you are to have a defect on it. So the larger the die, the lower your yield. So if you are now able to disaggregate your silicon, so it has a couple of really, really good advantages. Number one, everything that you put on a monolithic piece of silicon doesn't necessarily need to be made with the latest and greatest technology. There's only a very small area, maybe 50 to 100 millimeters squared, that needs to be on the latest and greatest fab node. So by disaggregating, what you can do is take this, which is most likely the CPU, mm-hmm. put it on your latest fab node, And since it's much, much smaller, you can pack more die onto the wafer. And since they're smaller and your defect density, you get better yield. And by getting more die per wafer and better yield, you have less wafer starts, and it starts to drive your cost down. And then for the other pieces of silicon, you can put them on more mature, older nodes that have incredibly good yield, and you can also reduce their size and get more die per wafer, and also reduce the cost there as well. So when you put those two things together, it's much, much cheaper to disaggregate your silicon than it is to keep them one big piece of monolithic silicon.
So when you start a process, let's say you start at least the thinking process from scratch, you're starting to think which transistor fits where. And where do you want your transistor to live, in which environment and which characterization of the process. And let's say that after you've digested how do you want to build that, then you are building a set of constraints which allows you to start and building the chip into the multiple dies. Now, when you look at the latest nodes, whether it's Intel or others, it becomes harder and harder to shrink. Yields are becoming harder. The characteristics are not scaling as they were in the past. And I'm talking about capacitance, area XY scaling, leakage, and so on. Power density becomes a problem. Building big dies has disadvantages because first, you may not want to invest your best transistor that costs you a lot on logic that may not get a lot out of it. That's one thing. The second, if you build bigger dies, your yield are decreasing, and then from financial perspective, you're starting to lose. And therefore, being able to take your important transistors into the latest node, the less important transistors to keep them on nodes that are a bit older, and to do this mix and match gives you a lot of freedom to deliver chip with the goodness that you want and with the right finance.
As I said, when you have the XPUs, when you need to have a good performance, for example, the best performance actually, you will go with the leading node because you want to be competitive. This leading node usually will have a higher cost, but it's important to put these IPs, of course, on the leading node. But there is also aspect of the scalability. So, for example, if you want to have in your family 3, 4 SKUs that have different number of cores, they vary only by the number of cores, then you want to have a core tile that you can replace the core tile and build a different SKU. It's allow you much better scalability than building several dies. So this is one thing. I/O die usually are a fixed frequency that you can hit even with maybe N-1 or N-2 process. Usually you put I/Os not on the leading node, for example, like USB, PCI Express, and such. And of course, there is always also the aspect of how do you build the family. It depends, how do you build the family, what SKUs you have in the family, what segments you need to support. This is once you see the full picture of the family, you decide how you want to disaggregate your part. So there are a lot of aspects, architectural aspect, cost aspect, design aspect, because also number of dies also translated to scope. And there are many teams that work on not just design, like the post-silicon teams and manufacturing team. So all these aspects influence where to put every IP.
And that's where you guys come in, because now you have to put all those two together, and that's when Foveros comes in. How does that work, and how challenging is it?
I would say Intel is very, very good at singulating silicon and sorting it. We have an incredible sort platform. So all of the silicon that is considered a top die that goes on top of the interposer, it's all die prepped first, which is a very mature technology. And we can also sort it. So only known good die are placed onto the wafer as it goes through the wafer level line to finish its processing. And then after it's finished, we have, we call it a stacked die. After the stacked die is singulated, you can sort it again. And then you can make sure that only good stacked die are going onto your package in assembly. And that can be extremely important. For client computing, on the package, you usually just have the stacked die and maybe some die side capacitors and things like that. But when you get into AI and some of the larger server platforms, you have very expensive memory that goes onto the package as well. So you can have anywhere between $400 and $1,400 of just memory on the package. So it's very important that the processor you're putting on there, the stacked die, it's known good. So then you can also increase your yields through assembly as well.
How do you select the different logic to the different dies that you have on the different processes? So actually it's a process, and it really depends what you build. So if you build a premium one, you could select the best process node that you have for all the transistors. It can be either a disaggregated type of construction with all the transistors on the best node, or a monolithic one. It really depends what you build and what is the size of what you've built. And this is what we have selected actually in Lunar Lake. When you're starting to look at volume and mass production, you have more constraints to look at. In addition to the scalability that you need to meet, you also need to meet different cost structures, okay? OEMs are building multiple types of machines. Some of them are cheaper than others. Some of them are more performing than others. When you want to build it, you want to build it in a way that it makes sense. The disaggregation process in which you select which logic to go into which die actually fits also there. And then you do the trade-offs of how do I maybe relax a bit the goodness of the product versus meeting the market needs of what the product, where the product is actually going to. And we are doing this process of doing the selection. So we will, in that way, build a broader set of devices that can go into broader set of families or platforms.
So you're doing all the testing, like for each tile, you're doing some testing at sort.
Yep.
And then once you start putting it together, you also do more.
Yes. So only known good goes into wafer level assembly, and then only known good from there goes into package assembly.
And what will be like the biggest challenges you can tell us about that you have run into? I mean, all this is very challenging, very complex, but something that stands out.
I would say the biggest thing is the throughput time. So for a traditional wafer, you can die prep it in a couple of days. You can assemble it onto a package in a couple of days. So you could probably from start to finish, from fab out to finish good out is maybe a week or two. But with wafer level, it does extend the throughput time because it does take a lot more time to assemble the stacked die prep it, sort it, and then get it into assembly. So I would say it probably increases the number of operations you have to do to get from start to finish probably tenfold. And it also increases the throughput time to about 3 to 4 weeks.
What are the challenges that disaggregation brings? So a good question, because with the goodies that disaggregation brings, it also brings some additional challenges. One is engineering challenges to actually deliver it. We need to develop IOs, and those IOs need to meet the characteristics that satisfy the performance of the product. We have multiple ways of doing the disaggregation. It could be over an organic way of connecting them, the old multi-chip package, connecting things through the package. It could be advanced packaging using Foveros technology, as we do in Panther Lake. Each of them has its pros and cons. If advanced packaging is very dense, you can go wide, you can shorten your latency, your bandwidths are good. If you're doing that over package, you have some other limitation like latency, like power, like meeting high-speed IOs designs that are usually harder. But as a whole, disaggregation, while it brings you the goodness with regards to flexibility and scalability, you need to compensate in some way on the latencies, bandwidth, as well as additional effort. So it does add challenge, as every good thing that we add, but it was worthwhile.
If you build the construction of the disaggregation in a way that it's scalable, then you use your building blocks in a way that you're building the family with maybe less die than as it looks in, I don't know, on the picture. But on the other side, disaggregation adds complexity. It's a more complex validation because you need to do cross-die validation or verification. You need a better collaboration and sync between the teams that own the dies So there is an aspect of complexity, but there is a lot of goodness from the disaggregation that you gain. Sometimes it can save scope, as I mentioned, but also allow you to build more parts with less dies.
What's next for Foveros? That you can tell us without secret sauce?
I think we're at a spot where Foveros is fairly mature. So we're ready for any external customer that comes and wants to run their platform on our Foveros line. So Foveros does rely on a solder connection between the top die and the base die. So our next offering is moving into wafer ODI, which is taking the base die and turning it into RDLs, which is a redistribution layer, and they're made out of copper and polyimide, so we can reduce the cost even lower. And that would be specifically for the products that have an inactive base die. We can just turn them into RDL lines and have an even better cost opportunity there as well. And I think after that, pitch scaling for Foveros is probably getting down to where you would maybe question where if we go too low, is it really worth the investment? And that's where HBI comes into play. So Foveros is a solder technology. HBI is a copper-to-copper bonding technology. Very similar in concept, stacking die on top of each other, but it's just a different interconnect for that interface for the top die to the base die.
The excitement's actually growing. The closer we get to our production commitment, shipping by the end of the year, the OEMs are like turning up the RPMs and turning up their energy to get more designs than we've ever seen before done on Panther Lake for AIPC.